So examples of the molecules with net dipole moment: water, methanol, ammonia. You see the lone pair that you draw out, it will drift towards that side because that's the most electronegative element here in the molecules, and also because it contains the lone pair that's not used for bonding. The D here, you know what the D is? The capital D here represents Dipole, okay? Dipole. So the mu is 1.85 Dipole dipole moment towards the oxygen here. Methanol 1.7, 1.47 for ammonia. You might want to compare between ammonia and water. Why is there higher value for water? Because oxygen is more electronegative. So what does it mean by dipole moment? It means that if you have a net dipole moment and you have certain panels that's charged around the atmosphere, okay? Let's say I'm the molecule. If I'm polar, that means I will tend to drift. I will drift. You see? Naturally, spontaneously. But if I'm like a benzene, I'm non-polar, no matter how strong the external electric field is, I'll be like a Buddha. No, not moving. Stationary, static. Numb. Okay, so that's the difference between having net dipole moment and no net dipole moment. See these molecules here? Very symmetrical, no net dipole moment. This term here, you have to know it, it's called resonance. Resonance in chemistry describes the localization of electrons here. That means you have pi orbital, lone pairs of electrons, they interact due to the orbital symmetry and right orientation, so the electrons can transit from the nearby orbital. Now if you take a look at the acetic ion, this is also known as ethanoate. It comes from your vinegar. Okay, we use this arrow, you see the double head arrow with a single line joined this way. This shows the resonance structure. So the negative charge of an acetic ion could be assigned to this green color oxygen or the pink color oxygen. So you see I have a reversal here, I can swap in any case I like. So if I do that, what happens is the double bond here goes across, then negative charge goes abroad. So they just switch, and it makes no difference in this case because they are the same element. You see, both oxygen connect to the same carbon. So it is very important to understand that in resonance structure, we do not change the connectivity of the elements. So we cannot say, I cut off the entire covalent bond, having a free atom or fragment, and join to another part of the same molecule. It doesn't work that way. Resonance, we only break pi bonds. Why pi bonds? Because the first covalent bond between all elements is the sigma bond. You see, I still have the sigma bond there that's intact, that's holding the two atoms in place, but the pi bond is additional to reinforce the bond. So if I break it, it's still fine because I'm still holding them together using a sigma bond. So the pi bond break, and then we take on negative charge, the pi bond goes over. That's how resonance work. Now, to be specific, the resonance structure, it is the average structure of these two forms. Okay, so these are called resonance form. These individual structures are not called resonance structure, they are called canonical structure. Okay, and we also have something called the resonance hybrid, average molecules that we can isolate from the different resonance forms of a drawing. So as you see from the electrostatic potential, it is unsurprising to see the red zone closer to the electronegative oxygen. And from here, what do we notice? This part is symmetrical. I can draw one line. It shows you that the negative charge does not reside to any single particular oxygen. It is the same. So this tells us that the negative charge will swap and move very quickly between the two oxygen atoms. So benzene has two equivalent resonance forms. You see the pi bond alternating pi bond, pi, sigma, pi, sigma, pi, sigma. You might be wondering, how come we can't draw it the other way? Of course you could. So instead of having pi bond between these two carbons, we can move it to the next guy. But once we move it, the rest going to follow like a domino door. You see, doors open, slam shut, right? So these are the two forms. and you see that it's very flowery, very symmetrical using the electrostatic potential map of benzene. Proven. Now, how to draw resonance forms? So there's a few rules here that you might want to follow, but I will just do it in my own words. So remember, these individual resonance forms are imaginary, they are not real. So if it makes sense to you, you follow the guideline, that'd be okay. Like carbon must have 4 bonds around it, 4 lines, if it doesn't have a charge. If it has a charge, then it can take 3 lines. Oxygen group 6 normally forms 2 bonds to 2 lines emerging out of it, but if I have a O plus, not my blood type, but O plus charge, then the oxygen can afford to take 3 covalent bonds. Now, normally when you see that you could draw a resonance form, it is when you observe that there's a charge like minus or plus and pi bonds. So you have to have pi bonds. Without pi bond, it is almost unimaginable to draw any resonance form. So what you can spot out is you have a pi bond, and then the other side is a sigma bond, and the first atom here has a charged particle. It could be negative, it could be positive in some other cases. So what you do is just swap them across, that's all. This arrowhead, you need to show it for chemistry majors, mechanisms, how electrons really move. So this lone pair here will push and go in between these 2 atoms to form the pi bond. You see later on it's formed, but the thing is, carbon can't form more than 4 bonds. It can't accommodate more than 8 electrons around it. It can't expand out that. So it has to break the other pi bond and push these pi electrons over to the oxygen. And now this green oxygen gains extra electron, and that's why it takes a negative charge. So you see how it works? And I can go back, take this lone pair of this green color oxygen, push it back to form a pi bond, breaking this pi bond off the pink color bond, go back here, and I get back that structure. Okay, likewise for benzene, arrow pushing, pi bond breaks, go to the next guy. Carbon can't contain more than 8 electrons in its valence shell, so push and push. You see, domino effect, I was saying just now. So you need pi electrons, very important.